Midterm is imminent, right? Next Wednesday, it's going to be over in Bechtel Auditorium. Okay, it'll.
This Wednesday.
This Wednesday. What'd I say?
Next Wednesday.
Ah. This Wednesday is the next Wednesday.
Yeah.
Okay. 2 days from now. We're going to have a midterm. It's going to be in Bechtel Auditorium. Come at, be sure to be there by 11:10. We'll start promptly at 11:10. We'll stop promptly at 12:30, hour and 20 minutes. I unfortunately won't be there. As I said, I'm flying out this afternoon, so it'll be.
You won't be there for office hour either? Who's going to have the office hour?
When? Wednesday. Yeah, I won't be there for office hours either. That's right. Unless you want to come to Washington, D.C., and I'll gladly do one. So maybe talk with the something like that. That's sorry about that. It was a command performance I couldn't use. Okay, so I went over the material last time. We haven't quite got the exam finished yet, so I'm going to have to, I can't stay in my office as long as I'd like to, but I'll stay in my office till like 1:15 today or so. So I'll go, right after class, I'll go, if we get kicked out of here because someone shows up, otherwise I'll just stay here. I'll stay there till 1:15 to get questions, or until no one's in my office, then I'll go down to the center and work on the midterm. Let me just say these things. Here's some guidelines for you. Be sure to try all the problems. Don't get stuck on one problem and just keep working at it and keep working at it. As soon as you find you're getting stuck, be sure to go to other problems, because you will get more points by doing partial things, no doubt, than getting a few right and missing and doing nothing on a bunch of them. Bottom line is this: when I'm grading and there's nothing on the page, there's no choice but to give 0 points, right? If there's something there. Now, if you just start writing random equations, you're still going to get 0 points, okay? But if you start attacking the problem and showing you're beginning to know something about this thing, then you'll get some partial credit. Try to show some work, because you do give lots of partial credit, okay? And show your work. Okay, I guess that's it. You can bring a calculator and bring your 1 page of notes, 2 sides. Okay, now bring a calculator, because there'll be calculations. Okay, any questions? Yes.
If we do run out of time, do you recommend writing out how we would solve the problem, and then we just don't have time to solve it? Or?
If you can put down some information that indicates that you understand something about the problem, it probably help. That's exactly right. Try to spend a little time on all of them for sure. I think that would be very helpful. Pardon? I always try to make time not an issue, and it sometimes doesn't work that way. But I try not to make it. We'll try to make it so that you should have enough time to do it. I mean, you know how I want you to solve these problems. If you have to write down, rederive all this, for the problems that we've done, input resistance of a common gate. The answer to that is R0 plus RD over 1 plus GM R0. You should know that. Don't rederiving that. I'm just not interested in, right? You should know all the answers. GM R naught squared for degeneration. Output resistance of the source degeneration. Know those answers. So, assuming that you know those, there may be some other little calculations go on, but then we'll take that into account. So you should not have a time problem if you know all the basic formulas and where to use them. Okay? Yes? Here's your mic. Oh, here's your mic.
Are the TAs going to set the exam? Because the way they set the homeworks are really laborious.
No, I'll do the exam. I will. Yeah, they are a little rough on you guys. I would agree. We do have discussions. So, I will. Exam is for me.
Do you have to use the full form of the equations in your notes, or just?
Good question. make approximation to within 10%. You will never be counted off if you make any approximation that's less than 10% from the right answer.
One of your tests said 1%. Is that just a typo?
Was that right?
Yeah.
It's a typo. No, never do that. I was feeling grumpy that day. Okay. Any other questions? Okay. We're probably okay on the homework, the frequency response homework. What we're going to do is extend that to the Friday of next week. Okay, so you get a couple of more days because I'm afraid you're not going to have all the information you need by end of the day. So we'll extend that. So the end of next week when the frequency response homework is due, and the project will go out that week. I'll tell you what I'm thinking about doing. I'll just give you a little insights on what we're probably going to do in that project, and I'll have to make sure this is going to work out. I haven't had a chance to think this through totally yet. But probably it's going to be the same circuit, same 1K ohm output resistance, pretty much the same DC specs that you had this time, except we're going to add a frequency response spec to it. So you'll be able to take your circuit you had this time and see how fast it really runs. Okay, so for those of you who got lots of gain by running it a nanoamp, you'll have to change things on the next round. So I think that'll be interesting. So, but anyway, at least you'll have the DC biasing stuff all figured out. Yeah, question? Mike.
When do we get our project?
When I finish grading them. I'm close. Actually, I work on the plane, and I've actually got pretty much all graded now. Just a few left, and now I have to enter them into the spreadsheet and do all that stuff. So they'll no doubt, for sure, will be done probably by later this evening before I get to Washington, D.C. In business class, I'll get free booze, so that's always a problem. Don't get quite so much work done in those days I do on other days. Right? Okay. Life of a professor, right? That's how it is, right? Okay. Frequency response. Let's do one more example Bode plot. Okay, let me do this one right here for you. Let me just, I did some other ones in the notes here. Let's do this one right here, this lower one. Okay, so here it is. It's a capacitor. Okay, so here it is. What is the Bode plots for this circuit right here? So how do you do it? Well, the first thing you need to do is to calculate the transfer function of this. So we make this, use 1 over j omega c for the capacitor. And what do we have? A voltage divider again. It's between R2 and this parallel combination of R1 and 1 over j omega c. So let's just do that. So it's R2 all over R2 plus the parallel combination of these two, and what's that? Well, it's R1 times 1 over j omega c over R1 plus 1 over j omega c. Let's multiply top and bottom of the second part by j omega c, so this is h of omega. And what do we get? This goes away, we get j omega c R1 plus 1. Okay, so it's R1 over that. Now I have 1 plus j omega c R1, the denominator here, so let's multiply that out. So we get R2 over R1, and this will be plus 1 plus j omega R1c, multiply top and bottom by that, and then I get R2 plus R1 plus R2 times 1 plus j omega R1c. Okay, so just manipulating this thing. Now, so what do I got here? So let's take this a little bit further. Okay, so I get, let's R2 times 1 plus j omega R1c over, so it's R1 plus R2 plus j omega r1 r2c. So what can you do with that? It's a mess, right? I mean, where's the poles? Where's the zeros? How can you plot this? How can we use our little formulas? You got to keep working with this thing to get it into the standard form where it's 1 plus, j omega over omega p, over 1 plus j omega over omega z times, some zero frequency gain. See, this form like this ends up, when omega equals 0, just a0. So the DC gain of this thing will be the term out front. And then you have these other zeros. Now, this part right here looks okay, right? 1 plus j omega over r1c. So looks like the 0 of this is going to be at omega z is going to be equal to 1 over r1c. So we can see that already. But the bottom, we can't figure out where the pole is. So I got to still keep working with this. I need to get things like 1. So what do I need to do? I need to divide by r1, factor out an r1 plus r2 out of the denominator. So let's do that. Let's factor out r1 plus r2 out of the denominator. Now I have 1 plus j omega r1c over factoring out r1 plus r2, and then I got a j omega r1 r2 over r1 plus r2 times c. And what is this? This is R1 in parallel with R2. So this thing has, so here we are. So we've done it. A0 is equal to this, R2 over R1 plus R2. The 0 is at 1 over R1C, and the pole is at 1 over R1 in parallel with R2 times C. Okay? Now we can look at this and we can see that the pole is going to be higher or lower frequency than the 0. Well, since R1's in parallel with R2, and this is just R1, that means R1 in parallel with R2 is going to be a smaller number than R1. So that means omega pole is going to be at a greater frequency than omega 0. So we can look at this and we can see that omega p is going to be greater than omega 0. Okay, that's kind of important. Okay. Now, we start off, so let's plot this now. Now let's do our Bode plots. So we start off with the 0. Now this is a 0 at finite frequency. It's not a 0. Actually, one more thing. Check the limits. Remember I told you about that, checking the limits? So what is the gain of this at low frequency? Low frequency, C is an open circuit, so it's just a divider between R2 and R1. R2 over R1 plus R2. And sure enough, that's what we have out front. At high frequency, what's the gain of this thing going to be? This becomes a short circuit, so this is going to be 1. So this thing should reduce to 1 at a very high frequency. So if you plug in for very high frequency, you can see this is R1, the 1's go away, J omegas and C's all cancel, and we get R1 times R2 over R1 plus R2 over R1 times R2 over R1 plus R2. Sure enough, it goes to 1. So you can check the limits. It's very good to do this kind of problems. Okay. Now, let's plot this. Let's plot the magnitude first. Okay. It starts off at very low frequency at A0, which is equal to R2 over R1 plus R2. The 0 is at a lower frequency than the pole, so this thing's going to increase in amplitude when we get to the 0. See, 0's in the numerator, right? And so it's going to happen, this thing will start going up when we get to the 0, and that'll be at omega 0, which is equal to 1 over R1 times C. The amplitude will increase, okay, and until we get to the pole location, which is at omega p, which is equal to 1 over R1 in parallel with R2 times C. And at this point right here, as we just calculated a minute ago, you can plug it in yourselves, you will find that this is a gain of 1. So this is what the magnitude of the h of omega looks like for this pole 0 plot. It actually goes up in amplitude. It starts below gain, below 1, ends up at a gain of 1. So things actually, it can increase with amplitude, even though it's a passive network. You just can't get more gain than 1. Okay? What does the phase plot look like? Now, what's the phase shift we're getting from this 0? Notice the phase shift here is going to be plus. So we get a plus 90 degrees when the omega gets large, looking at this 0. Zeros can also be negative. You also can get negative phase shift from zeros. Okay? When we do stability, you can't get negative phase shift from a pole or positive phase shift from a pole, right? It's plus here, but no, it's in the denominator, right? So it ends up with a negative phase shift. And the problem, the reason you can't do it is because a pole, a negative phase shift in a pole means it's a pole in the right half plane. This is an S plane, right? This is j omega. This is sigma. If you have a pole in the right half plane, this is S of a S domain. What that means is if you impulse that or have some noise, your response is an exponentially increasing signal if it's a pole right on the axis, right? Well, that means that you have instability, right? So poles all have to be in the left half plane. And that means they're all stable. That means you don't, any impulse response, if it's on the axis, will be a decaying exponential, not an increasing exponential. So that's part of our stability thing. We'll make sure that all our poles are in the left half plane. If the pole is right on the axis, then you have an oscillator. Okay? Zeros can be anywhere. They can be in the left half plane, they can be in the right half plane. There's no stability problem from that. So you can get positive or negative phase shift from a zero. And that turns out to be important to us later on. This one, it's going to be positive phase shift. Okay, so how do we plot that? Well, we plot it, we said, okay, here's omega z at 1/10 of omega z. Whoops. I can't have positive phase shift if I start at the top of the page. Okay, so here's 0 degrees. We have omega z. At 1/10 of omega z, we start getting a positive phase shift. Will be 40 plus 45 degrees at the 0, and we'll get up to 90 degrees at 10 times the 0. Okay. Now we get over to the pole. Let's say the pole is sitting way out here. At 1/10 of the pole, we start to get negative phase shift. At the pole, we'll be at 45 degrees, and at 10 times the pole, we'll be down to 0 degrees again. So this is what the phase shift looks like. Goes up to 90 degrees and comes back down again. And if these poles are closer together, of course, this going up and going down might look like something like this. If they were close, it might just, I mean, it'd never get up to plus 90 degrees, right? It could do something like this. If this was, you know, 0.1 omega z, and this is 10 omega p. Okay?
Can you explain the left half plane, the right half plane thing?
Left half plane? Right half plane. Okay. Review your solutions of differential equation problems. Okay, so what we're talking about here is solving the differential equations associated with a LC or I mean, what is a capacitor? How do you realize it? Well, the way we realize it, it's kind of the differentiation of the voltage, right? The current through a capacitor is equal to C times dV dt, the voltage across the capacitor dt. So really what we're doing, this phasor analysis stuff, is all about solutions of these differential equations in a very simplified form, because if we say that Vc is really associated with a sine wave, right? Then what we can say is that dVc dt, right, ends up with omega times sine of omega t. And that omega right here, okay, is the same as the omega we talk about with that impedance, right, j omega c. That omega and the omega coming from this differentiation. So it's all about solving the differential equations. Now, when we jump to S, now this is solving the differential equations for the special case of sine waves. When we work with Laplace transform transfer functions, in other words, if I have a formula that looks like this, 1 plus s over sp, okay, let's say this is my Laplace transform equation, this h of s. To go back and forth between h of s, I should say this, h of omega is equal to h of s evaluated at s equal j omega. That's how we go back and forth between That's how we go back and forth. We evaluate h of s at s equal j omega, and that's how we get the frequency domain response. Okay, that's just don't want to go more in that right now, but that's how you go back and forth. But h of s is the more general case. Okay? All right, so now. Okay, so let's say we have this is our transfer function. If we impulse this, if you take the Fourier the Laplace transform of impulse is h of s. Let's say I want to get the response r of s, right? It's equal h of s times your impulse of s, the Laplace transform of the impulse response, right? Which is a 1. Okay, so basically what we have is Laplace transform of this is 1, and if we do the inverse Laplace transform of this whole thing, we'll find out what the response, the time response is. Okay, so we'll take the impulse inverse Laplace transform of this thing to get the time response, and if you take it to this equation here, you end up with something that looks like this: e to the minus sp times t, I think, right? I don't know if that's right units. Okay, all right. So this is the impulse response. This is h of t equals this with some amplitude in front of it, a1 or something like that. Okay. Sp is, so this is for this is the response to an impulse. If we impulse this, if Sp is positive, which means the poles over in the right half plane, this thing, our impulse response, will have an exponentially rising value. If it's on the left, if it's on poles are negative, plus. Should be plus here, I guess. Okay, right. It's a positive value for Sp, it'll get rising value. If Sp is negative, we'll get a decaying value. So it's what we're doing is the Laplace transform is a strategy to get to the solution of the differential equations. You can see the stability from it. So all you have to do is look to see if those poles are the right or left half plane. You can tell whether this thing is exponentially increasing signals or exponentially decreasing.
What about on the axis itself, you said?
Then it's just marginal. Then you're not increasing, you're not decreasing. So it ends up, if this is the j omega axis, this is omega 0. If you have, it'll be complex poles. You always need poles to be real. The overall transfer function has to be real because you have real variable values coming in. So if the poles are sitting, they always come in complex conjugate pairs because you have real circuit elements. So this right here means this thing is basically oscillating right at this frequency. So it's an oscillator at that value. So it's not increasing, not decreasing, it just sits and oscillates. Okay? All right. Depending on whether the pole is greater than or less than that 0, you can see that the amplitude could go up or go down. For the case that we had for this circuit, the thing went up, right? If for that circuit, it always would. But other circuits, you basically have poles and zeros. Amplitudes can decrease or decrease depending on the relative value of the poles and zeros. We'll have to worry about that later on. That's it for Bode plots and Laplace transforms and everything else. I can more than happy to go over this more in office hours and stuff like that, but I'm not going to do more in class. So any more questions about that? We'll get back to this Laplace transform thing some more. This stability thing we'll be talking about some more. Okay? All right. Here's why we're talking about all this stuff. The new model. We're going to increase the model, our transistor now, to have capacitances. Before we had no frequency-dependent elements. Now we will. And this is all the elements that a transistor has, and it's a bunch of them, as you can see. There's a capacitance from the gate to the bulk. These should be connected together right here. Okay. So this is connected. So there's a capacitance from the source to the substrate, the drain to the substrate, the gate to the substrate, from the gate to the source, and from the gate to the drain. These things are, let me just quickly talk about where they come from. I'm not going to do too much here. So this, let's say this is a NMOS transistor. Here's the oxide. Here's the P-type substrate. Here's the source and drain. So this is source, this is drain. Here's the gate. Okay, source to bulk. This is the bulk down here. This is B. Okay. Source to bulk is this diffusion. We're connected to the source diffusion, N plus. The complicated thing about this diffusion is it has two components to it. If we blow up this diffusion thing, it looks like this. It's actually very wide and very flat. So there's a per unit area formula for component of this capacitance, this source to bulk capacitance. So let's call this the area of the source. So multiply times area of the source times the junction capacitance of the source, right? That's this number right here. So that's kind of this number there. There's also a number, if we look at the top view of a transistor, so let me do a top view for a second. This is the gate. Here's the source. Here's the drain. The top view, so there's the periphery is around this side. There's the area underneath it, and that's this bottom plate area, right? But then there's this periphery on the source, on the side away from the gate. So it's like three sides here. So this is the width of the transistor. So it'll be width plus two numbers here associated with the minimum length that you can, the narrowness of the diffusion you can have, right? So it's W plus 2 times this diffusion width. That's the peripheral. That turns out to be very high capacitance, much higher than the bottom plate. So we're talking about the edges here, right? The reason that's high because the doping levels are much higher up here. This is N plus and P plus, and this is P down here. So it's N plus to P is a lower, the difference between, if you have two highly doped regions like this, the capacitance is quite large. When it's high to low, it's not so different. Okay, not so high. So we have a number here of this value on what the capacitance is on the periphery area, right? These are all numbers you'll have to be given as part of the device model. Okay, so for the source and drain, there's a sidewall capacitance. That's what I'm just talking about on 3 of the sides, and then there's a area capacitance, which is associated with the area of the source. Okay. There's a capacitance associated with this overlap right here. That capacitance is this little teeny overlap right here between the gate and the source and the gate and the drain. Think, why do we worry about that? The reason we worry about that one is because in saturation, all of the channel is connected to the source. So CGS is very large in saturation. Cgd doesn't see the gate capacitance at all. This is a lot of capacitance because the gate, that's a really big area and that's a very thin oxide region here. This channel charge is only connected to the source, not to the drain. The only capacitance you see in the drain is the gate to source overlap. It's this little teeny overlap thing right here. So gate to drain is very small. So C gate to drain is usually much, much less than gate to source, C gate to source. Why do we care about it? It turns out this capacitance is in the worst possible spot. Even though it's really small, it really hurts us a lot. The gate to source is huge, but it turns out it's in a place where it doesn't hurt us as much. And I'll explain why in a few seconds, why I say that. This gate to drain to bulk and source to bulk are pretty good sized capacitors, not as large as gate to source. They're larger than the gate to drain. Okay? And you have to worry about them. But they're not in a particularly bad spot. They don't get any weird effects. The gate to bulk is usually quite small. It's just a little region of overlap here on these two ends. So it's usually pretty small too. Sometimes you worry about it. So the biggie is this one. This is one of the really small ones, but it's in a bad spot. And these other ones just kind of come along for the ride. They just make your life miserable. Okay. C gate to source overlap is that little overlap right here. Gate to drain overlaps, a little overlap here. And see, it's farads per meter. So you multiply this times the W to get the absolute value of the capacitance. Okay. C aux is the area, that's the gate capacitance. That's CGS. That's the area underneath the gate. That's this region here. And since the charge distribution is not uniform across the gate to source region, it's not like you just take C oxide capacitance times W times L, because there's no charge near the drain end, and there's lots of charge near the gate end. So there's a factor that you multiply this time, which is a function of the charge distribution in the channel, and you end up with something like 2/3. I think it works out to be. Okay. When you're in linear region operation, then the charge, the gate to source and the gate to drain both are connected to the channel. We have no pinch-off region anymore. It's not saturation. Then what happens is the charge kind of gets distributed between the gate to source and gate to drain regions. So the bottom line is, depending on what region of operation you're in, you see different capacitances, okay? And here's the reason why you often want to stay in saturation, because as soon as you go into linear region, you start seeing a lot of capacitance on this drain to source end. And I'll tell you, that's a bad place for capacitance to show up. It really hurts. It's amplified by the gain of your stage, and I'll show you why that's true in a second. The equations for this are fairly nonlinear. Okay, so here's gate to source. It's a 2/3 thing I just talked about, times C gate to source overlap times the width. Gate to drain is just this gate to drain overlap times W. Source to bulk. So here's that junction capacitance. Here's the area of the source. And here's the voltage dependence. VB bulk to source to some power, MJ, which is also a parameter that you have to get from the process. Okay. This is for the area. That's the area region. This is the sidewall. This is the stuff on the edges, times the perimeter of the source on those three sides that you have to worry about. Okay. SPICE uses a half for this value for the bulk region and 1/3 for the sidewall capacitance. So it's really complicated, messy stuff. You can sort of see you just don't want to do any hand calculations with these capacitors. Okay. You sort of get a rough idea, basically what they are at the nominal bias condition, and just treat them as fixed values, because there's just no way you're going to deal with all these nonlinearities in these capacitances. Okay. Here I've shown, these are design rules. In other words, the minimum width 2 lambda, for ours 2 lambda equals 0.13 micron. Generally, all the other, this is the source and drain contact. This is a contact of metallization into the diffusion. And there'll be a minimum size of that. And it depends on the process. Here what I've said is it's about, that will, if this is 2 lambda 0.13 micron from across this length of the transistor, then I'm saying that the opening that makes the contact of the to the diffusion has to be 2 lambda. And there has to be at least a lambda spacing on each side of this. So you end up with at least minimum 4 lambda of distance. And this lambda is just a parameter that characterizes all the design rules. Okay, this is very simple design rules. Design rules these days are much more complicated than this, and you just have to learn them if you're going to lay something out, right? So you can sort of see how I calculated the perimeter of the source and all. Minimum size. You can sort of see why a minimum size device isn't W over L equal to 1. Right? This is W over L equal to 2. Its minimum size is sort of set equal to 2 because the source contact, you have to be able to get metal down contacting that diffusion, and it has to have some spacing around it. So you end up with W over L equal to 2. It's sort of the minimum size transistor. If you really put all, we've just been saying, okay, just look at W over times L is the area of the transistor, but in actual fact, there's some other constraints. When you do your models now, you got to put in the area of the source and the area of the drain, perimeter of the source, perimeter of the drain. We'll decide how much of these you'll have to work with. These are now a function of the size of the transistor. So you see, as you make the transistor bigger, these areas of the source is going to get bigger, the area of the drain will get bigger, all right? Perimeters will get bigger. And L and W, of course, L times W gets bigger, so once W gets bigger, then that increases CGD overlap, and all those capacitance get bigger. So you got to put these numbers in. You will have very fast circuits if you do not put in these numbers, right? Because what SPICE will default to some very small value. So if your circuits start running at multiple gigahertz, you probably have forgot to put in the actual areas of the transistors, okay, right? If your circuit only works at 0.1 hertz, you probably use the wrong units, right? Instead of pico micron, 10 to the minus 12th microns, or 10 to the minus 12th meters, you might have had 10 to the 12th meters or something like that, right? So you can make some huge errors here if you don't get the units right and make sure that you put in all the different areas and perimeter values correctly, okay? So if you don't put in L equal to 2 and W equal to 1, I think SPICE might default to meter. That means you have a transistor 1 meter in length and 2 meters in width or something like that, right? So obviously you get some pretty slow circuits. So get those parameters right. Okay, that's the new model. Capacitance is everywhere, okay? Now, what capacitance does not show up here? If you look at this, there's no significant capacitance between the source and drain. Just about every place else, but nothing coupling the source to drain. And that turns out to be really good, really helpful to us. Okay, everything else has capacitance to it. Okay? Yes.
Can you explain why the CGD is in a bad place here?
Excellent question. Absolutely. Let's do that next. Right. Yes, exactly right. Here's why. Okay, this is CGD is something we will fight against big time. Okay, and here's why it happens. Okay, here's the problem. Let's take a simple circuit. Let's take a circuit like an amplifier with a capacitor across it. And why do I choose this circuit? If we think about So let me not, here's VN, good old common source, bread and butter gain stage, right? Let's assume I got an ideal current source up here and not worry about the capacitance associated with that. Let's only worry about the gate to drain capacitance. Here's that CGD overlap thing. Let's only worry about that one for right now, okay? So what do I have here? This is an amplifier with a capacitor across it, right? So let me, and it's an inverting amplifier. So let me redraw this like this. An amplifier with a capacitor across it. So I'm claiming this circuit is the same as this circuit, okay? All I'm including is a CGD by itself. Here's an input drive to that transistor, and here's the output, okay? Here's the question. Here is what's strange, and it's called the Miller effect, okay? The Miller approximation. Here's the problem. Let's do an equivalent circuit looking into here of this circuit that has a capacitance across the gain stage. Let's figure out from the input side, let's figure out an equivalent sized capacitor which will have the same current going into it. This is I test, right? Same I test going into it, coming from the same V test as this circuit has. What is this capacitor? Well, here's how we have to do is V out is equal to minus A times V in. That's just basically the formula for the gain stage, right? But now let's use our real formula differential equation for the capacitance current. IC, the current through the capacitor, is equal to C times D times the voltage across the capacitor. And the voltage across the capacitor is going to be V in minus V out. Okay, this voltage minus this voltage. Okay, so I defined VC in that direction. Okay, so IC is equal to C times the voltage across the capacitor. The voltage across the capacitor VC is equal to V in minus V out.
Shouldn't that be V in A times V?
No, this is V in on this side.
Right. I mean, when you have V in plus A times V out.
V out equals minus A times V in.
Right. So on second equation, it should be V in plus A times V in instead of.
Oh, right here. It means right here. Yeah. Yes. Right. Yes. Thank you. Okay. So I replace V out by minus A times V in. I get this formula here. Now I can factor out V in, which I did here, and I factor out the 1 plus A, which is here. So with this, look at this formula here. IC equals C times 1 plus A. So let's call this C Miller. times the Vn dt. It's just as if we had the input current is just as if we had an amplifier with no capacitor across it, but an input capacitance of size C times 1 plus the gain. Let's say our gain is 1,000. Our input, this little CGD thing, will be amplified by the amount of gain that we have in this stage. That's the problem. As we ask for more gain, this little CGD is going to get amplified by that amount of gain. Okay? And you can sort of see this can be a big problem. So this little CGD gets this big amplification factor. Let's look at some of the other ones. Let's look at CGS. Here's CGS going to ground. CGS would be right here. Well, CGS is just in parallel with this. So the input capacitance we'll see is CGS plus C times 1 plus the gain. And there's a CGB, right? Okay, so CGB, that's the one that goes C gate to, let's say we ground the bulk. CGB, well that's just also in parallel. CGB with this C times 1 plus A. What about C gate to source? I'm going to do it ready. What about C? Okay, so you can sort of see the input capacitance here of this stage is going to be equal to CGS plus CGD times 1 plus A plus CGB. Why does this happen? Let's go back and look at this for a second. Just make sure you understand this. Okay. So let's put a little test voltage here. What happens when we put a little test voltage here? This gets amplified, and on the output here, we get a big swing from a little teeny input. So what's happening across this capacitor? We put a little teeny voltage here. All of a sudden, the output swings like crazy. This little teeny goes up, and the output goes down like this, right? We're going to have to supply a lot of current into this capacitor, right? Because all of a sudden we've seen a big voltage change across this capacitor here. So it's like this capacitor is much, much bigger. Same thing happens with a resistor. Let's say you put a resistor across here. Okay? Let's look at the current of that resistor. What's going to happen? We put a little V in. We think this size R. What's the voltage? What's the current that's going to go in? It's going to be V in, minus V out divided by R. Well, what's V out? V out is equals V in plus A times V in minus V out, right? Over R equals I in. And this is going to be equal, we can take this and we can write this as equal to V in over R divided by 1 plus A. So putting a resistor across here, across the gain stage, we'll end up having the resistance look 1 plus A times smaller because of the big voltage change across it. Okay? That's the Miller effect. Now, what does this mean for us? Should I do a little 2 or 3 minute break here? Let's do a little 2 or 3 minute break. Then I'll come back. Use
For this circuit, can I just say that that's the common source? And then that right here is like a source follower, so it'll be approximately equal to this times the gain of this.
Yes.
I can say that? like V out is really? I can say that?
Yeah, that's right.
Okay, but why? Because there's all this crap on the top. Like, why is that changing?
All that crap is just for purposes of, remember, this is the load up there, right? This is
Right. So
all this crap is setting the DC bias. Okay, so it's a voltage divider.
Testing. Testing.
Working? Can I use it? Mike? Okay. Let's go on. So a couple of good questions there. Let's do another example. It's one that's kind of interesting. Okay. We'll do this again. I like my big black pins. Okay, C gate to source for this one. Here's V out, and here's V in. What's going to happen with Miller on this one? C gate to source. Okay, so it's kind of the same sort of thing. We're going across the gain stage, but here the gain is positive, equal to plus 1 or something near that, right? Let's say it's equal to plus 1 to start with. If equal to plus 1, we plug in our little formula. It's C times 1 plus A, but A, remember, was the magnitude of the negative gain. So it's going to be 1 minus, is 1 plus A, but A is the magnitude of the negative gain. So it's going to be, let's talk, this is positive gain, so it's going to be 1 minus 1, okay, or is equal to 0. So with a gain of plus 1, a capacitor across a gain of plus 1, we see an effective Miller capacitance of 0. That make sense? Yeah. Why does it make sense? That means V out tracks V in. That means I have this go up and this goes up. The voltage across the capacitor never changes. Voltage across the capacitor never changes, no current. So we don't even see the capacitance there. So in effect, across here we get, basically if it's a positive gain of 1, we see the capacitance just is basically eliminated from, you'll see it. So a common drain, even though the CG gate to source is really huge, isn't a big problem for us. What about our gate to drain? It goes up to the positive supply. So it adds a little capacitance hanging off the input, but this side's grounded. So it just is just a little load capacitance connected to our input. Have to be driven from the other side back there. What about, let's look at all the other ones. Here's drain to bulk, C drain to bulk. Is that an important capacitor? If the signal never changes on it, then it's not, you can just ignore it. So that's going to help you a lot. When you put in what capacitors to worry about, look for ones where the signal is swinging, where the signal's changing. And particularly where the signal's changing a lot is really the biggest problem. The areas where there's lots of gain, that's where you have lots of trouble. So this one causes no trouble. What about right here? Here's C source to bulk. Well, that's loading down the output. That's connected right to the output. Yeah, so that's one we got to worry about. Okay. What's the other one? There's C gate to bulk. That's usually pretty small, but so it just hangs off the input just like C gate to drain does. So a lot of capacitance will collapse, depending on the topology, will collapse to be the same one. So we end up with something that looks like C gate to drain plus C gate to bulk plus C times 1 minus the gain of this stage, right? CGS will be the input capacitance, right? Then we have a capacitance on the output here, that's current source, of C source to bulk. Okay. Now, yeah.
I'm sorry, why is minus one minus the gain again?
Why is it 1 minus 1? That little business there. Because when I did this before, remember when I did this? I said the gain was minus A. So I end up with a capacitance value of C times 1 plus A is the C Miller, right? So A is the magnitude of the negative gain, right? So if I have a gain of plus 1, A is going to be equal to minus 1, right? Okay. What happens if it's not quite? What the gain of this circuit we know with body effect, if I didn't tie this bulk back to the source, A is equal to 1 over 1 plus chi, right? So what's that going to be equal to? Well, for this circuit, it's A equals minus this, right? Let me, okay, so this will go up equal to C times 1 minus 1 over 1 plus chi, which is equal to C times chi over 1 plus chi. So if the gain isn't exactly 1, you have it a little less than 1, then you'll end up with a little formula like this for what C Miller is. Okay. So going across high gain, negative gain stages, you get big amplification. Going across a small positive gain, you're okay. If you go across a large positive gain, let's say this is, let's make this A equal to plus 10. If we put a capacitance feedback around a large positive gain, what happens? This is positive feedback, probably of instability. Okay, so you end up not generally having gain feedback, something around a large positive gain. So it's either negative gain, which is negative feedback, which is fine. Okay. Yes.
Is there something where you have C times 1 plus A to the negative 1?
Yeah. Okay, so now we've been talking, let me do that. Okay, so what we've been talking about here, let's do this again. Okay, here's minus A. I've been talking about how things look from the input. Okay? Now if there's lots of gain, what about how things look from the output? Okay? In this Miller approximation, it decouples the input and output. Now it's not entirely accurate because if there's finite impedance levels, this is kind of an ideal amplifier, infinite input impedance and zero output impedance, then what I say is true. If I have finite output impedance and a finite input impedance, I can't decouple the input and output like I just did. Okay? But assuming that this is a low output impedance and a high, well, what can we say? We can do something on the output. So we said this on the input side is the same as having a capacitor of size C times 1 plus A. What about, can we say what might be equivalent looking from the output? Well, if the gain is large, in other words, this is swinging a lot and this is swinging very little, the input looks like it's almost like a ground. So I think the best approximation is just to call this C if you have any reasonable amount of gain. Okay? To be more rigorous in some strange sense, you know, what you can do is, let's solve for sort of the reverse Miller approximation. Okay. The problem I'm saying with this is that if you have finite input impedance, this approximation isn't quite so accurate. So if you don't, you shouldn't be real dependent on this. But, whoops, sorry. Dependent in the sense that, I mean, unlikely, you know, well, what's the answer? Let's look into here. So this is, this is V out. This is A V out over A, right? So this is the gain. This is the negative, and this is the in reverse direction, right? This is what input is equal to, right? Okay. I guess minus this, right? Okay. So what's the voltage across the capacitor? It's equal to V out minus a minus V out over A, right? Well, this is equal to V out times 1 plus 1 over A. If I go into my little formula, I out, okay? This is, I'm driving with a V test, basically. Here's an I test, driving from a V test at the output. I test is going to be equal to C times dVc dt, and this is Vc. This is equal to C times 1 plus 1 over A dV out dt, or dVt dt. So this capacitor right here is of size C times 1 plus 1 over A. But if A is large, right, this goes away and you just have back to C again. Right? Okay, so it's kind of the output Miller. Yeah.
But if A is less than 1 and the gain is like an inverting gain, then you get like a negative capacitance. And then what does that mean?
If A is less than 1. So let's say we have 0.2 here for A. Now see, that's kind of why I said, now what's happening, if the gain's less than 1, changing the output, this decoupling of the input and output across this Miller capacitor is not valid. I mean, what kind of circuit do we have now? We've got, the gain is so small. I don't know, how do you make gain that small? But, you know, what we're saying is that if we change the output, we're changing the input substantially, and those two are tracking, and so there's not a nice, you can't decouple things like this. So that's kind of why I say, for that limit, is why I don't like to think about this in reverse Miller thing, right? Because the approximation of eliminating the feedback through this, if there's really a small gain, is kind of not very useful. Okay, so I'd say assume that the gain, this Miller approximation works when the gain's reasonably large, and you don't have to worry about this value here. It's not a significant effort. At least assume it's greater than 10 at least, or something like that.
So you wouldn't have to deal with circuits where the gain is really small.
You can't use the Miller approximation to figure out what the capacitance is on the output, I think is the answer. You have to do something more accurate. Okay. Okay. All right. Little insight now into what, so here's, now, how do we use this? Here's a inverter. Here's an input resistance. Now, if we have a voltage driving this node, It doesn't matter what size capacitor we have, we'll have no problem, right? In other words, if I look at this circuit right here, the size, the input Miller capacitor C times 1 plus A, and if I have a voltage source driving this node, there's no attenuation of the input. This capacitor could be infinite in size because the voltage source will just keep pumping out current, will make this voltage change as it's needed. Okay? The problem comes in when we have a finite source impedance, an Rin. Because what happens then, as this capacitor gets bigger and bigger, what do we have? We've got a voltage divider. It's the old one-pole response, an R and a C. So the signal right here is going to be the voltage division between the input and the voltage we see at the Vx. Let's call it right there. So it's a one-pole response. So here's the circuit here with a finite input resistance. Here's what happens after we do the Miller approximation. The gain of this circuit's GMR out. Now we're getting into another big approximation. C times 1 plus GMR out is the size of this capacitor. Notice what I've done here. This is the low frequency gain. This is kind of the essence of the Miller approximation, is the fact that you use the low frequency gain in this little formula right here. As you saw from my analysis, what causes this Miller approximation to happen is the gain from here to here. So what happens if this gain is a function of frequency as well? And it certainly will be, right? Because there's capacitance hanging off this node, right? So this gain, and there's the C itself. So this gain is actually a function of frequency. The Miller approximation is basically to use the low frequency value. Okay? Which is okay. You just, when you have, you'll see when it begins to get in trouble. It certainly gives you some insights into what's going on. It gets you in, here's when it gets into trouble. It gets into trouble when the poles associated with the output are on the same order of frequency as the pole associated with the input. In other words, it's the relative placement of the poles which is a really important number. And that's what makes this frequency response stuff so complicated. Okay? Its fact is, if a pole at the output, let's say I have a really giant capacitor out here. Really big capacitor. Okay, right. That's a big capacitor. Okay, right. And it's bigger than, much, much bigger. This C output capacitor, we'll call it, is much, much greater than C Miller, this capacitor we have right here. What's going to happen? And if RL is large, and this is a huge capacitor, that's going to kill the gain. There'll be no gain here. That means C Miller, this value here, at the frequency of interest here, and what's the frequency of interest? It's going to be 1 over Rn times this C Miller, and this is C Miller. So at this frequency, the gain is going to be 0. The gain is going to be 0. That means that this term here really shouldn't be there. I shouldn't have used the DC gain here because this gain is going to be killed by this output, this very, very large output impedance. So what you need to look for, or look at, is the placement of the poles. There's an input pole associated with this Rn and this capacitor here. There's kind of an output pole, and the output pole here is going to be equal to, using this reverse Miller thing, we could say it's equal to C, plus any other capacitance hanging here. Let's call it C drain to bulk. C plus C drain to bulk. And the resistance associated with that output is going to be RL and R naught. Now, why do I say that? It's a voltage divider on the input. You can sort of see why the signal here is smaller than the signal here. As you go up in frequency, and this impedance here gets smaller and smaller, you can see that the gain is going to go down. Why do we see that in the output? Let me show you in the output. Here's RL. We have a C output, which is equal to C gate to drain plus C, gate to C drain to bulk. Okay? And that goes to ground. I'm sort of doing this. We have the Miller approximation here, right? C Miller. See, the nice thing about this Miller, it decouples the input from the output. Now, what is the resistance of the output here? Let's just find what R out is. Now it's going to be Z out. Z out will be equal to RL in parallel with R0 just like before, but now it's going to be in parallel with 1 over j omega C out. Okay? Let's just simplify this a little bit. Let's say RL is much, much less than R0, because I just don't want to mess with that, but you can do this yourself if you want to. So I end up with RL is in parallel with 1 over j omega C out. Let's multiply that out. RL times 1 over j omega C out over RL plus 1 over j omega C out. Let's multiply top and bottom by j omega C out. I get RL over 1 plus j omega RL times C out. So this is what Z out is equal to. Look at that. That's the pole. What's the gain of this circuit? It's going to be the gain, AG, will be equal to G sub M times Z out, minus that. You can sort of see it's going to be minus GM times RL over 1 plus j omega RL C out. So what is this? This is a pole at 1 over RL times C out. So we call this kind of the output pole. So this pole associated here is the output pole. It comes from the fact that we're reducing the amount of output impedance. So it just acts like another, like a load. I mean, just like your RL did in your project, right? Remember how that reduced the gain? Well, that's what this capacitor does. It reduces the gain, and then, unfortunately, it reduces the gain more and more as they go up in frequency. That's why these things are so nasty, right? More frequency. This could be connected to another stage, right? Let's say another common source stage. What's going to be on this node as well? The CGS of this second stage, CGS of the second stage, right? Plus the CGD of this stage, but that's going to be Miller multiplied by the gain of this second stage. So this output capacitor, C out, could end up looking like C Miller of the first stage. Not C Miller, just C, this CGD, I'm sorry, C gate to drain of the first stage, okay, plus C drain to bulk of the first stage, plus C gate to source of the second stage, plus C gate to drain times 1 plus GM RL of the second stage, GM2 of the second stage. So this is the Miller multiplied gate to drain capacitance. Plus what else? Plus C gate to bulk of the second stage. So this is all the output capacitance associated with this output node, and it's in parallel, and so you end up with this pole being at all these output values with the impedance, the resistance on this node, which is R0 in parallel with RL. So the way you do these things, you find the input capacitance. You use Miller approximation to sort of break down the coupling to the output. You'll find the input resistance. In fact, if you work this out, let's say I have a resistance right here. It's in the notes there. You can do that. R, for whatever reason, there's a resistance to ground. RG. It was there. You will find that the pole on this input will be equal to 1 over Rn in parallel with Rg times C Miller, whatever it is, okay? So it's all the resistance on this node and times the capacitance on all the capacitance on that node to ground. The output is all the resistance on that node times all the capacitance on that node to ground. That's where the output pole will be. So we kind of talk about an input pole, which is a voltage divider, and an output pole, which is associated with the output impedance. Now, once you do this, you've calculated the voltage right on this node. So there's no more voltage divider you have to worry about. And then what you do is you go to the output of this stage and find its pole. So there's, for this circuit here, there'd be a pole here on this intermediate node, which is kind of the input pole of the second stage and the output pole of the first stage. And those are coupled together. It's the same pole. And there's a third pole associated with the output of this stage right here. That's what your homework's all about. Right? Okay, you get that? I'll do this over and over again, more examples, but that's the key thing. But let me show you why this Miller approximation is so important. Here's the gate to bulk, gate to source, gate to drain, and drain capacitance. So here's a bunch of all the capacitance associated with this one here. Let me get rid of a few of these, because this problem is almost unmanageable, right? Let me get rid of the CD for a second. I said ignored, usually not possible. That's right. I mean, unfortunately, this is not true, but we'll work with ways to approximate all this stuff. But let me get rid of that for a second. Let me just use CGB, CGS, and CGD. That's this formula right here. Let's call CG equal to sum of these two together. It's a simplified formula. Without the CD, let me solve this exactly. I end up with two poles. Okay? Here's that Miller capacitor thing. I'm solving it, and here's what I end up with. This is the exact solution, not using Miller approximation. I end up with two poles and a zero. Well, if you use the Miller approximation, we didn't have any zero. Where do zeros come from? Zeros are very painful. Zeros kind of pop in, they foul up your analysis big time, and they're really difficult to figure out where they are, okay? So I'll kind of point out where some really important ones are, but sometimes when you do a new circuit, you may get some zeros, and it'll be very difficult to analyze. Here's where they come from. They come from feed forward. The zero is coming from the fact that the signal here is actually feeding forward into this output. So it's where the Miller approximation totally breaks down. The Miller approximation says you can replace this capacitor with a capacitor to ground, but you can't, because this input is actually capacitively dividing between CGD and the output impedance on this node. Okay? That gives rise to a zero. So when I do this problem exactly like I did here, I end up with this, and the zero is at Gm over CGD. It's Gm of this transistor times this capacitor, times this capacitance here. So this is where the zero is at. It's a right half plane zero, and we get two poles that show up from this circuit. One pole is 1 over Rn times C Miller. So this is exactly the Miller pole that we've been talking about. C Miller is that 1 plus, C Miller. So this is I'm relating back to what I just did a second ago, right? Is equal to 1 plus Gm times R out times CGD. So this looks just like what we kind of expected from the Miller approximation. But there's another pole at minus Gm over Cg. And that has to do, again, with some coupling between the input and output, which doesn't show up in the Miller approximation. Now, fortunately, this pole is really high frequency. It's what is it at? It's at 1 over Cg times 1 over Gm. Well, Gm is really a small value, right? This pole, Rn, is usually pretty big. C Miller's got this Miller multiplication effect, so this pole is at a very much lower frequency. So often we can ignore this pole. This zero is at a pretty high frequency too, right? It's at 1 over CGD times 1 over Gm. So it's at a pretty high frequency too, so we don't have to worry about it. So we only usually have to worry about this one here. But it's not that these guys aren't around. And here's the problem. When you run SPICE, SPICE will calculate all the poles and zeros for you in your circuit. It will find a lot of poles and zeros, okay? Most of them aren't very important, okay? But part of your job is going to be, it's like the old approximation we talked about before. What are ones you have to worry about and what are ones you can ignore? In this frequency response stuff, doing this simplification stuff is really critical. And let me give you the bottom line of all this. Bottom line of all this is frequency response calculations are very tough to do by hand. I will be happy in the final exam when I do give you problems to solve by hand. You will get full credit in some cases if you get the answer within a factor of 10. Right? You will be off by 5 orders of magnitude and be happy with your answer. Right? Not realizing you're off, okay? So these frequency response things are really much, much more difficult. The approximation of 10% now is way too tight. We will now be very happy with factors of 2 and 3 compared to your SPICE results. Okay? Where does it come from? It comes from this nonlinear voltage dependencies of the capacitors that are just too painful for you to calculate by hand. It comes from all this kind of approximation that we do because these problems get too complicated too fast, right? I mean, this thing already looks like this, right? What happens when we put this CD thing back in again? It's a cubic, and you almost can't solve it. Yeah.
How do we know which ones are good to ignore? You will tell us?
You will learn, right? Yeah, that's the point of this course, is what can you ignore and what can you not ignore. That's the most important thing you have to do here. So, Rob, what have we here? Here are the old homeworks that you have not picked up yet. So if you want to, all of them, I guess.
All of them. Besides homework 4.
So if you want your old homework, here's a chance to get it. Okay?
Professor, you said the words goes off. It depends on nonlinear voltage dependence.
Nonlinear dependence of the capacitances. The fact that things like the Miller approximation aren't valid. There's a frequency dependence to it. There's coupling between the inputs and outputs. And there's, when the poles get near each other, then there's interaction between the poles that are very difficult to analyze.
Thank you very much.
One of your past exam questions. Over here, this is a Wilson current source, and when you're calculating the output resistance, the approximate reacts to be 0. Why can't you do that?
Because it's only a 1 over GM, right? So it's a pretty small resistance, right?
Oh, okay.
Compared to this R's. The reason I'm doing that is I'm worrying about this formula right here, right? VT is equal to R04 times the current through R0.